Hello, everybody. Great. Well, good to see you tonight. I hope that you guys are having a great evening. I'm Po-Shen, and welcome to the official collaboration with Math Kangaroo. Now, it's a particular pleasure to work with all of them at Math Kangaroo because their questions are really, really creative. I should say that as some of you know, I'm a math professor at Carnegie Mellon University, and I've also been for 10 years the coach of the US Math Olympiad team. That was before. But I've seen lots and lots of different questions, and the Math Kangaroo ones are ones that you really have to come up with another idea to think about, which is why we love working with them. Now, today, you'll notice that we have a very interesting setup. And the interesting setup is not me because I'm currently here at University of California, San Diego, where I was just doing some math lecture to the students for around in this region. Instead, actually, we have two extraordinary high school students who have learned how to teach in a very, very captivating way. Now, the important thing is in this class, you should talk as much as you can. So they will tell you more, but we have something called chat relay. And the more ideas that you send into it, the better of a class this is going to be, especially because everyone here is going to react to your comments, okay? So we're looking forward today to doing levels 5 and 6, I think. And with that, I'm going to toss it over to Arya and Evan. Go for it.
Hello. It is good to see you all. And as Professor Lowe mentioned, please send your messages in chat to the person named Chat Relay. Then they will show up on screen and we will be able to react to them. I saw beforehand a lot of you guys had already worked this out. So hit on mute and please don't hesitate to message one of the co-hosts of the meeting if you need help. Anyways, my excellent co-instructor for today is named Arya, and he has been involved in math competitions since 8th grade, so quite young, and he has also qualified for the Amy. He coaches his local middle school's math counts team, and besides math, he enjoys listening to music and playing chess. And so give it up for Arya.
Hi, I'm Arya, to put in face to the things that Evan just said. And let me introduce Evan real quick. Evan is also amazing. He is big into STEM as a whole. Not only has he qualified for the Math Olympiad, he's qualified for the national level of the Chemistry Olympiad as well, and the Physics Olympiad. So very impressive, very nice. And apart from that, he loves dabbling with 3D printing, which is very interesting. So yeah, that's Evan. You want to say something so you pop back on screen?
Hello. Thank you for that introduction, Arya. And I saw a really good question in chat already by Plum asking what the stars are for. And so our moderators will give you stars for sending good messages in chat. Like people saying hi right now, those are good messages. So you get stars for them. Later, you'll get stars for sending in answers and explanations for the questions that are on screen. And next to the stars, well, that's your star count. For example, Edison already has 3 stars, and Jean-Marc already has 2. So does George. Well, George has 3, if I can read. I don't know. They're very small numbers on my end. Either way, the more stars, the better. Cool. Shall we get started, Arya?
Sure. Wait, real quick before we get started, I'm always curious like where people are from and like how old you are when you do these live solves. So if you don't
Yeah.
mind, just like typing maybe what state you're from, so we get to see the demographic of the people here.
Oh, wow. We've got
TN.
people from all over. This is excellent. I see some people from Oregon, Canada, Rivet Island, Rhode Island, and Washington as well. Fun. I also see people from Houston, Maryland. Wow, and Waterloo.
We got a wide array, like wide.
Yeah. Where are you from, Arya?
Oh, Minnesota. I'm from Minnesota. That's
Oh,
crazy.
Minnesota,
Hello.
home of the ice or something. I don't know. I've always
10,000
wanted to
lakes.
visit
We
Minnesota.
have a lot of lakes here.
Cool. Oh, I wonder, do we have anyone from Nevada? That would be really nice, since I am from Nevada. Oh, Marina, same. Taylor Swift is epic, as they say.
Agreed. I
Oh,
like Taylor Swift.
CC went to Nevada. I'll count it as good enough. We've got full-blooded Nevadans here, so excellent.
I've only been to Vegas. I've never been to Reno.
Fair enough. Yeah. most people have. Like, for most people, the map of Nevada is, okay, we've got this strange shape. You've got Las Vegas. You've got Reno. I don't know, and maybe you have aliens. So,
I think that's pretty accurate.
ooh, I see some really excellent questions about infinity from Ari Hunt. Let's save those for after the live session. I really like them. Let's see. Or maybe one of our moderators will answer them for you. So keep an eye on the screen and maybe you'll see an answer roll by soon. Alrighty. Arya, what do you say we get into the math?
Yeah, sounds good. Let's get started with problem one. Okay, quick note. In these live solves, we're not going to go through every single problem, so you'll see the problem like numbers jumping around, but we'll roughly get more difficult as the live solve goes on. But let me just move my face out of the way and let's get started. Matchsticks can be used to build numbers as shown. For example, to build the number 15, one needs 7 matchsticks. Because yeah, okay. As they have shown here, 1 has 2 matchsticks, and then 5 uses 1, 2, 3, 4, 5. So 2 plus 5 is 7. What one needs the same number of matchsticks to build the number 8. It uses 7 matchsticks. What is the largest positive number that can be built with 7 matchsticks? Well, my first thought here is that the more digits you have, the bigger the number is. So let's just first try to get as many digits as we can. And to do that, we're going to want to pick numbers that have a relatively like low number of matchsticks in each digit. And then we can build the number from there. So I'm just going to go through each number and just label how many matchsticks it uses. So then I can pick the smallest ones. 0, for example, has 6. We did 1 is 2. 2 has 1, 2, 3, 4, 5. 3 also has 5. 4 has 4. 5 has 5. 6 has 6. 7 has 3. 8 has 7. That's a lot. 5, 6. Okay, 9 has 6. So as you can see, like we don't want to pick 8 because that already uses 7 matchsticks. So we can only have 8. And using that logic, we're going to want to use smaller numbers. So I see 1 and 7 are the smallest. So now what I'm going to do is try to figure out how many ways I can pick 7s and 1s to add up to 8. I mean, 7s and 1s, but the matchstick numbers are 2 and 3. So how many ways can I add 2s and 3s to make 8 and then figure out the biggest number out of that combination? So right away we have 332 as the biggest 3-digit combination. And I can't do 4 digits because, or I can do 4 digits actually. Can I? Okay, I can't do 4 digits because I want to use 7 matchsticks. This is important. So if I were to do a 4-digit number, I would need at least 8 matchsticks, which is not allowed. So 7, I'm going to use at most 3 matchsticks. And as we can see, I'd want to do 771, but this uses 8 matchsticks. So this is also not good. So let's decrease one of them to a 2. So now I have 322, which is a 7, 1, and a 1. And since I want the biggest number possible, we're going to put the 7 in the hundredths place, the 1 and the 1. And this adds up to 7. So we use 7 matchsticks, giving us an answer of 711.
Yeah, nice. Another way, like when I was solving it alongside you, I was just thinking, really, I want the largest left digit as possible, the largest hundreds digit I can get. And I don't really care what the next 2 digits are. Because, well, I suppose informed by the answer choice, I could say if I can get a 7 or 8 as one of the hundreds digits, I'm done. But also in general, the hundreds digit matters more than the tens and ones digit for this sort
This
of
is
thing.
true.
Yeah. Alrighty. Let us move on from the matches and get to I presume these are kangaroos. Kangaroos playing, let's say, soccer on a cube. Let us see. And we're asked to fold this cube up, this net. These are what these 2D shapes are called. This net into a cube and see what's what. That is, specifically, we want to see which answer choice is possible. Now, I'm going to zoom in slightly because this is hard on my eyes. And I notice right away something that is interesting, which is that all these kangaroos are facing different directions. And I actually think this is the point of the problem. We want to see the directions the kangaroos are facing. At first, I thought it might have been like, which colors can you have next to each other? Because, for example, you couldn't have like blue, blue, and yellow as you're viewing the cube because you only have one blue, three greens, and two yellows. But of course, if this was the only thing we'd care about, then quite a few of these would be possible. And I see a good point in chat from Risha, who says the two kangaroos are facing the same direction. Yes, let's focus on the direction the kangaroos are facing. First of all, let me just mark this square with an X. The square that has, yellow, blue, and green coming together at the same spot. This square is over here in this photo, over here in this photo. Well, actually, not necessarily. They might not be. So I'm not going to do it. But I think it's a good idea to consider the direction of the blue kangaroo relative to the yellow kangaroo, because we see that this is different every single time, the blue and the yellow. Right? Let's see. So when I fold this up, if I imagine folding this up into a cube, so let's just call this our center square over here. Well, the blue kangaroo faces towards the center square. The blue kangaroo faces towards the green, and the yellow kangaroo faces away from the center square. So when we fold this up, it will look like the blue and yellow kangaroo, these blue and yellow kangaroos are facing the opposite direction. And it'll look like this kangaroo is facing sideways if we orient it such that this square is on the bottom. So going back here, I notice right away that option B looks like it satisfies this because we have opposite blue and yellow. And I know right away option D does not satisfy it because we have the two yellow kangaroos facing the opposite direction. But this is not what happens. If we look here, we see that from the perspective of this green square, one of the kangaroos is facing up and one of the kangaroos is facing side. So D is definitely wrong. And similarly for E, we have the blue and the yellow kangaroo. Oh, wait, no. E could be possible. The only problem is, though, if we imagine unrolling E, then when you take down the green square over here, then you unfold the blue square. You'd have that the blue guy is facing sideways rather than facing towards the green square. So E is not possible. Similarly for B, the blue kangaroo is not facing directly towards the green square. So, nah. Well, at this point, we can see that that B works. So this is probably our answer. But for the fun of it, let's see why A doesn't work. Oh, of course, A doesn't work because we've got the two yellow kangaroos. The two yellow kangaroos need to face at 90 degrees or whatever. But no, they're facing with their heads towards each other. And this is not allowed. The head of one of the yellow kangaroos should be facing towards the front side of the other yellow kangaroo. So, oops. A is not. We say B. Yeah, basically the answer is B, and we're right. Okay, that's good. I guess for this problem, which is honestly a kind of tricky 3D visualization problem, unless you write it down, the job is to look at where the blue kangaroo is facing and then where the yellow kangaroo is facing, where the direction of their head relative to other kangaroos is very, I would say the easiest way I can think of at the moment of doing this. Cool.
Awesome. Okay, I think that was a great explanation. Let's move on to the next problem, which is number 6. Let me move this out of the way real quick. Okay. Anna has 5 circular discs of different sizes. She wants to build a tower of 4 discs so that each disc in her tower is smaller than the disc immediately below it. How many different towers could Anna build? Okay. She wants to build it. Okay. So it seems like all 5 of these discs are different sizes. So we can just number them. I'm going to number them because it's easier to visualize, or think about the different sizes, and bigger number means bigger size. And we want each of her tower of 4 discs so that it goes like big to small. Oh, am I writing on my face? No. Okay, that's good. Each disc in her tower is smaller than the disc immediately below it. Okay, so we're going big to small. And I guess the important thing to see here is that whenever I pick 4 discs, there's only one, since all of them are different sizes, there's only one way to arrange those 4 discs in a way such that it goes big to small. For example, let's say I pick 1, 3, I don't like 2, so we're going to skip 2. Let's say these are my 4 sizes of discs. The only way that Anna can build her tower is going 5 to 4 to 3 to 1. We're arranging them in decreasing order. And for any 4, there's only one way to arrange them in decreasing order. So the answer is the number of ways to pick four items out of these 5 items. And as some of you know, that would just be 5 choose 4. But if you don't know what 5 choose 4 is, we can think about it like this. Let's say I have like 4 slots here. Oh, I'm off my screen. Oops. Okay, let me just write it over here. Okay, so if you know what 5 choose 4 is, the answer is just 5. But if you don't know what 5 choose 4 is, let's say I have 4 slots representing the 4 items I want to pick. I could pick any of 5 things for the first one, 4 things for the second one, 3 things for the third one, or 2 things for the second one, right? Because let's say I pick 1, I only have 4 options left. So that's where the 4 comes from. And then we can keep taking 1 out as we pick 1. And we're done. We pick 4 things. The only problem with this, however, is when I'm picking 4 items, I don't care if I pick the 3 at like the 3rd spot or the 1st spot. So I need to divide out all the possible ways to pick the numbers like 1, 3, 4, 5 in any order. And the number of ways I can arrange this list would be like placing the 5 anywhere. For example, I have 4 ways to place where the 5 goes in any of the 4 places. But then once we place the 5, I only have 4 ways to pick. I only have 3 ways to pick where the 4 would go. So I have 3 for that. Similarly, 2 for the 3, and then 1 for the 1. So I have 4 times 3 times 2 times 1 ways to like order this list of items. So I want to divide out 4 times 3 times 2 times 1. And some of you may know this is known as 4 factorial, but that's not really important to understanding this. So when we divide this out, as you can see, we get 5. So yeah. Oh, I'm off screen again. Oops. There we go. 5.
Yeah. This is a good way of thinking about it. That the order is fixed. So it's like we have a stack of 5, 4, 3, 2, 1, and we only want 4 of them. So the answer would be choose 4.
Okay,
I
actually,
just thought of another way.
Oh, okay. I think you might
say
be
it,
thinking
Arya.
about
I
this.
don't want to steal your thunder.
I was just about to say, you could think about this by just picking the one disk you're not going to include, which is much simpler than what I just did. And obviously, you can, out of the 5, you can pick one of the 5 to not include in your tower. And that's a much easier way of getting to the answer of 5.
Yeah, this is fun. Yeah. And it is. So we shall hop on to the next question, in which Alice has apparently some puzzle pieces and needs to combine them to form a hexagon. Let's see. I'm not sure how well these are showing up, but alrighty. Cool. They are showing up vaguely. But either way, we've got these puzzle pieces, and we want them to combine to form a hexagon. So I think a good first step would be drawing the full hexagon over each of these pieces to see what the shape of the thing that is missing looks like. So for example, for piece 1, we'd complete the hexagon like this. For piece 2, we'd complete the hexagon like, let's see, 2, like this. Here we go. And for piece 3, we'd complete the hexagon like this. Now, oh, we should also complete it for piece 4, I suppose. Piece 4, it's something like this, not to scale. But either way, right away, like people are saying, we can eliminate option 2 because, well, it looks like option 2 requires 3 pieces of things because, well, these 2 regions are completely disjoint. So option 2 is not possible. Let's see. Option 3 and option 4 look the most promising, as well as option 1. But this is because 2 of them are going to be correct. We'll be able to fill 2 of them with the other. So let's perhaps look slightly closer at this shape that we cut out for option 1. Well, the shape is precisely option 3. So we can just slide in option 3 to fit option 1. And, well, we can see that option 4 definitely does not work, because if you look at the bottom here, the bottom will not fit in with the cutout at the bottom for option 1. So option 4 also does not work. And we're left with, option 1 and option 3, which we can verify do indeed fit together to form this hexagon. In fact, I think we could even draw out the way they fit to form this hexagon. Here we go, like this. Not to skip, but this part is too long. Either way, like people have been saying in chat, answer choice B, which is pieces 1 and 3. And so hopefully Alice is happy, because we were correct. It is option 1. Nice. Excellent participation in chat, everyone. This is really fun when you guys are putting in all these answers and ideas. And Siddharth has noticed a pattern. They claim it might always be answer B. I don't know. Is the next question also answer B, Arya?
Let's find out. That'd be quite interesting if it was. I once had a teacher that made a test about 90% the same answer, just for fun. It was an interesting test-taking experience. Anyway, okay, let's get started. Jacob glued the 3 pieces of paper shown onto the white circle at the right. Which of the following patterns could he not obtain? Okay. He glued the 3 pieces of paper on the... Okay, this is interesting. So as you can see, none of these actually have a whole gray semicircle. So what I'm guessing he did, or what he must have done, is taken, like, if this is our semicircle, he must have glued some of the like black quarter circles on top of here, like this, so they get deleted. And another observation I'm seeing is that in all, okay, actually, this is not true. Not in all of our answer choices, but he glued the 3 pieces. Okay, in, like, for example, in this answer choice, we have 2 of the whole like black pieces showing, and they're not on top of each other. So if I was Jacob and I'm drawing my circle, I'd first start with the gray part, right? Because that's on the bottom. And like, let's say yellow is my gray. So I'd start with this. And then I'd want to put like 1 black quarter circle here and cover that up with blue, and then another quarter circle here and cover that up with blue. So as we can see, this is not the answer because we can pick it. And similarly with like, for example, if we take E, this is very achievable because we can start with the gray semicircle and then just put the black quarter circles on top, since they're not in each other's way per se, right? Because we see the quarter circle on the bottom, and then I'm gonna put this, like, the blue ones just in the way that I have to in order to make the picture work, which is gonna be something like that. So what I'm looking for is somewhere where I see like the quarter circles being glued in such a way that it can't be this on the bottom or something like that. Like, for example, this B and E are like the same case, right? I start with the semicircle and then I'm going to glue the black stuff on top. So this is also works. And this one's a bit tricky. If you can't see it right away, it doesn't hurt to draw it out to make sure. But this is also achievable because what we're going to do is see how, like, this semicircle, if we were to pretend that it was like X-ray vision, that it would extend here. So what's going on is he first started with like a gray, like a quarter circle here on the bottom. And then he put the semicircle on top of that. which is like right here. And that covered up. That's how we get that weird like 1/8 looking sector of like black. And then he put like a quarter circle here at the end. This is also achievable. And now by doing all these examples, we kind of see how C is not going to be able to be made. It's because if you look at like the gray portion here, if like the black sector is glued on top of the gray, we need this whole sector to be gray in order for this to work. But we only have a semicircle. We don't have this much of a gray portion, and we don't like cut pieces of paper or anything. So in order for this to be achievable, we'd need all of this to be gray on the bottom, which can't happen. So C is the one he can't do. And unfortunately, that's not B. So
Very sad. That is very sad. Yeah, but I agree. It is quite comical to imagine Jacob putting down this semicircle and then somehow having it take up 3/4 of the circle. So yeah, definitely option C. But now we're away from Jacob's and we've walked down the street to the Potter's house. And the Potters on Privet Drive have a patio which is tiled with square tiles of 3 different sizes. The smallest square. Let me pause for a second and circle the word square because this is important for later. The smallest square has a perimeter of 80 centimeters and a snake rests on the patio, as shown in the diagram. What is the length of this snake? So this tiny square has a perimeter of 80 centimeters. So of course, its side length will be 80 divided by 4 or 20 centimeters. And I'm just going to put a yellow tick for every 20 centimeters I see. So there's one here. It's a square. All of these are 20 centimeters. And this is also one of the tiny squares. So these are also 20 centimeters. But then, something funny happens. Now we know that this square has a side length of twice 20 centimeters. That is 40 centimeters. So this length is also 40 centimeters. This length is also 40 centimeters. More relevantly, this length of the snake is 40 centimeters. We can continue doing this for each of these 3 squares because now that we know this side of the square, we know this side of the square, so we know this side of the square, and so we know that side of the square as well. But then something fun happens. I see a question from Rakuram. Where is the snake? Let me draw the snake in green to make it clear. We have the snake wind around the patio. I've got to say, this snake is quite the impressive specimen. Most snakes I know do not turn at precise right angles, but to each snake their own. And I see lots of people are saying it's option C, so I could just circle C and move on because I trust you guys to be smart and get it right. But I want to also solve it myself. I want the fun of it. Anyways, we know that this has a side length of 20 centimeters. This tiny square here, these tiny squares all have a side length of 20 centimeters. And so this section over here is 20 centimeters. So this larger square has a side length of 60 centimeters, like I saw in chat earlier. I see people are becoming more confident about option C, and I'm inclined to agree with you now. So let's see, 60 centimeters, another 60 centimeters, and then 20, 20, 20. So let's finish by counting it up. How many 20 centimeters do we have? 20 centimeters. Well, we've got one. Actually, let's just add it up like normal people. 20, 40. Well, 20 plus 20, plus 40, plus 40, plus 40, plus 40, plus 40, plus 60, plus 60, plus 20 times 3, which is just another 6. These 3 represent 20. And yeah, I'm going to definitely pair these 6 numbers off to form 300s. And well, now we've got an 80 and a 20, that's 100. So now we have 400. Another 20 gives us 420, our answer of C. So yeah, the people who are saying it's C with no doubt in their minds are correct. It is, in fact, option C. Cool. Nicely done. Nicely done.
okay. Um, let's move on to the next one. And we've jumped to number 14. Oh, you can't see it, but it says 14. It's a bit cut off. Anyway, let's get started. We're dealing with Maria, Peter, Richard, and Tina, who were playing football in the classroom and broke a window. That does not seem like a very good idea. I don't recommend playing football inside of a classroom. Anyway, when the principal asked who did it, she got the following responses. Oh, okay, this seems interesting. Maria said it was Peter. Richard said, Peter said it was Richard. Richard said it wasn't me, and Tina said it wasn't me. Only one child was telling the truth. Who broke the window? Okay, this is quite important. Only one person was telling the truth, which means out of these 4 statements, 3 of them are lies.
And this is the problem with kids these days. They don't tell the truth enough.
Evan, I might have to remind you, but you're also a kid.
Oh, dang it. Shoot. I was lying.
Anyway, 3 lies, okay? And oh, okay. Actually, I see something interesting here. We see both Richard and Tina both say it wasn't me. One of them has to be lying. And whoever is lying is the one who did it, right? So we already know that it must be Richard or Tina, which means that these 2 automatically have to be liars because one of these guys is telling the truth. Wait, what? Yes, one of these guys is telling the truth and one of them is lying, and then these 2 are automatically lying. So if it was Peter and that's a lie, it's not Peter. But we already know that because it has to be Tina and Richard. Peter says it was Richard, but we know this has to be a lie. So it wasn't Richard. And also Peter cannot, it has to be one of Richard and Tina, but we know from Peter's statement it wasn't Richard, therefore it must be Tina, if that makes sense. Okay, let's recap because that was a bit confusing and I kind of went through that quite fast. Okay, it must be one of these 2 because they both have the same statement, Richard or Tina. Maria says it wasn't Peter, which is obvious. We already know it has to be Richard or Tina. And it was Peter, so that's a lie. Peter says it was Richard, which must be a lie as well, because one of these has to be the truth. So this is a lie. But since he says it was Richard, which is a lie, it wasn't Richard is the truth, because that's the opposite. So if it wasn't Richard is the truth, Richard is just not the person. So we're left with Tina being the person who broke the window, and Richard is the person who told the truth. Okay, awesome.
Yeah, I agree with Jocelyn. Tina is in big trouble. But to be fair, I feel like Maria and Peter should also be in big trouble for lying, which is also bad. So I suppose their lying is less egregious than Tina's, because Tina says, like, I didn't do it. And then they're lying. Okay, no. Falsely implicating other people is bad. Don't do that. Just as falsely saying you didn't do a crime when you did do it is bad.
Maybe
Be
just
honest, folks.
don't break windows. I think
That
that's
too.
the best solution.
Actually, yeah, this is a much better moral. Rather than being honest when crimes are committed, do
Don't
not
commit the
commit crimes.
crime.
Yeah, exactly. Or else you'll have to paint windows, also known as rectangles. And Lucas is coloring these rectangles with 3 colors, and he wants every rectangle that is next to each other to be a different color. How many ways can we do this? Okay, let's just play around for a little. I noticed that as soon as we pick the colors of 2 of these rectangles, we're done, basically. And here's why. Let's say we take this rectangle to be red. Then this rectangle down here can be blue or yellow. It does not yet. Let's say it's yellow. Well, then this rectangle cannot be red or yellow because the red and yellow rectangles are next to it. So it's got to be blue, which blends in quite well with my wall. And now this rectangle here, though, cannot be blue or yellow because its neighbors are blue and yellow. So it's got to be red. And similarly, this top rectangle here has got to be yellow. Yeah, I see. Yeah, good. Nice. I see some people are actually responding in chat with what colors these are. So that's really good. But yeah, once we said this is red and this is yellow, everything followed suit. So we do have three options for this first rectangle of color, three color options. Then we have two color options for this rectangle. But once these two are colored, that determines the color of this rectangle, so we've only got one option for that. Similarly, once these two are colored, we only have one option for this rectangle, so that leaves us one here. And finally, these two rectangles being colored give us, well, no choice for this rectangle. In other words, we only have 3 times 2, which is 6 options. Yeah, very good. And let us see if 6 is correct. It is. So it is option D. And we have more variety amongst the answer choices, which is great. Oh yeah, and I saw someone ask a few seconds ago whether we have seen these problems before. Fun aspect of these live streams is that Arya and I have not seen these problems before. On our screen is the first time we're seeing them. So you get to see our thinking process all the way through. Oh, and I see someone didn't understand. So I'll quickly go through again. That's a good thing to ask. So let's say I colored this rectangle red. And well, I'll start with that. Then the next rectangle here, I can do whatever I like with it, except make it red. It can't be red because then we'd have 2 red rectangles next to each other, and that's no-no. So let's say I make it yellow. Well, then this rectangle over here, this one, it's next to a red one and a yellow one. So it can't be red and it can't be yellow, so it has to be green. Sorry, so it has to be blue. That's not blue, that's yellow. So it has to be blue. And then we can do a similar thing for this rectangle, which is next to a yellow, and so can't be yellow, and next to a blue rectangle, so can't be blue. So it must be a red rectangle. And so finally, the rectangle up in this corner would have to be yellow. Yeah. And as an exercise, you could try doing this if you had made the first one yellow and the second one, I don't know, blue. This would work the exact same way. Or as a bonus exercise, you could do the same with these 2 rectangles and see how the problem progresses. You end up with the same answer though, of D, 6 options. Good questions, everyone.
Okay, before we move on, I saw 2 questions I want to address. One question is, someone asked again, how do you get stars? And Evan explained at the beginning of the live stream. But just to reiterate, you get stars by basically saying anything that is like somewhat productive. It doesn't have to necessarily, like, these are great problems. I would give that a star. You know what? Bringing positivity into the chat. So yeah, say anything basically that is not like negative, downright negative, and you get a star. And it's fun to get stars, you know? I saw someone with 43 stars. That's a lot of stars. Second, someone asked, how do you solve these so fast? And I'm pretty sure I can speak for Evan when I say this, but it's just through practice and solving a bunch of problems. I've solved a bunch of problems. Evan has solved a bunch of problems. And at some point, you kind of gain an intuition or idea of where to begin on problems because you've solved so many of them. And that's about it.
I agree. Like, it's not some magic innate ability. This is definitely not the case. It is more like, how do, I don't know, pro tennis players play tennis? Because they've put in many hours of practice. Of course, I don't solve math nearly as well as pro tennis players can play tennis. But there is still that element of, if you practice, eventually you can start recognizing patterns in how to be successful at this thing you are doing.
If you want a more concrete example, like the problem Evan just did with the colors, I can think off the top of my head at least 2 problems from 2 contests I've done that use the same idea of, and actually after the live stream, I'll pull up the problem, but it was on the AMC like 2 years ago or a year ago, and it's basically like the same idea. And even if you get a problem that's not the same idea, you'll somehow be able to like mix ideas from stuff you've done and figure out how to solve new problems. And it just comes to practice. Anyway, I'm getting a bit off track. Let's get back to the kangaroos and the rabbits and a beaver in this case. Okay, those 3 animals are having a competition. The beaver moves 1 space at a time. The rabbit moves 2 spaces at a time. and the kangaroo moves 3 spaces at a time. They all start from the start point, which is right here. Ooh, that's a big circle. Okay, let's underline it. The start point. The winner is the animal who lands exactly on the point marked finish. Okay. In the smallest number of complete moves, who wins the competition? This is interesting. So, the beaver moves 1 space at a time, the rabbit moves 2 spaces at a time, and the kangaroo moves 3 spaces at a time. So they're gonna have to move like a net total if we're counting as steps. Like for example, the beaver is just gonna take 1 step at a time. So he's gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 steps he gets to finish. So let's see if anyone can do it faster. Let's say the rabbit is the number 2 guy. So he's going to move 2 steps at a time. So 1, and then 2. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and we see a problem here. We've gone 5 times, but he has to jump 2 spaces every single time. So he's going to skip finish line here, and he's going to go here. And this is a problem, right? Because now we're 6 moves and we've passed the finish line. We need to go all the way around before we can get back, like get another chance at it. So we're going to go 6, 7, 8, 9, 10, 11. Ooh. I feel like I must have messed up somewhere. Okay. Perhaps. Okay. As you can see, he gets back to the start here, which means he's just going to keep going around the circle forever, hitting like all the even numbers, but then never hitting 11 here. So to me, it seems like the rabbit never makes it to the finish line. Now, let's see what the kangaroo is doing and give him a new color. Let's say he's purple. So he's going to go 3, then 6, then 9. He's going to skip here. So he goes 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10, 11. He also makes it an 11. So that means that both the kangaroo and the beaver make it in 11 steps, and the rabbit's going to be jumping forever. Another way to think about this is, like, I guess an easier way. This is how, like, maybe if you don't know where to start, I'd recommend just, drawing it out and see where you go. But if you have, like, a good foothold or you've seen this type of problems before, the way, like, I think about it immediately is I have to make 11 steps to get there. And I think about how many like steps there are in the circle, and since this is like half perfectly, there's like 22 total dots on the circle. So if I'm the rabbit and I'm jumping an even number of steps every time, I go 2, 4, 8, 6, 8, 10, all the way to 22, and then I go back. I'm never gonna hit an odd number step because I'm only jumping by 2. So the rabbit immediately just never hits 11. Like if we numbered these like 1, 2, 3, 4, 5, all the way around up to this one being 22, the rabbit only hits even numbered things. So we're never going to get to 11. If I'm the beaver is obvious. We just go 1, 1, 1, and 11 times I'll hit 11. And then for the other one, I'm going to want to like go around the circle as like 22 times x, where x is the number of times I go around the circle, plus 11, because I want to like finish at 11. And I want this to equal like 3 times some number. I'll just say k. I want this to be a multiple of 3 because the kangaroo is going to be jumping in 3s. This is how I think about the problem. And well, we see like when x is equal to 1, this is 33, and 33 divides 3 divides 33, so k equals 11. Oh, that's a 1. K equals 11. So that's another way of thinking about it, but the idea is the same. But yeah. Oh, all of that was covered by chat. I'm so sorry. Hopefully that made sense. Evan is writing it out in a different form, which would you like to explain?
This is actually a really powerful form of reasoning, that there's a multiple of 22 different between two things, that actually means they're equivalent mod 22. So for example, let's say 0 and 22. Well, of course, they're like equivalent mod 22. They have the same remainder when you divide them by 22. Same with 1 and 23 and 45 and 67. All of these have the same remainder of 1 when you divide them by 22. And so we say that they're equivalent mod 22. And they're actually nice things we can do now that we have this in a funny little equation form. But we draw 3 lines to indicate equivalent. Yeah, this is actually called modular arithmetic. And if you're interested in this, you can take, I think we cover this more in depth in module 5, number theory, the course offered by Daily Challenge. So I would highly recommend that course. It's my personal favorite. But either way, in this question, we're asked to find k's, the smallest k, such that 3 times k is equivalent to 11 mod 22. That is, he's gone around the circle some number of times and 11 times past that. In other words, he's gotten to the finish line. That's 11 around the circle from the start. And so, well, it's difficult to divide by 3 here. We can't do what we would like to do. What, the k is equivalent to 11 divided by 3 mod 22? What does that mean? Okay, he gets there in 11/3 jumps. So we actually have to do something more fun to solve this. But that perhaps gets us even further off track. Either way, this is the form of the equation you would solve in modular arithmetic. And another good way to write this problem down. But yeah, either way,
Nothing, go finish your
sorry. Yeah, but either way, we would still get the smallest solution of k is 11 here, because 33 is equivalent to 11 mod 22.
I was just going to say, like, if you're interested, just search up modular arithmetic in Google, and probably one of the first 5 results will explain everything Evan was just talking about in more detail.
Oh, that is also good. Google is powerful. Yes.
But take the Daily Challenge course. Highly recommend. We might be one of your teachers.
Yeah. And how fun would that be? Really fun. We would get the gears in your mind turning whenever we meet. Speaking of gears turning, totally an unintended pun. We've got some gears and some pulleys, and we want to know the 2 boxes that move upwards. Righto. I hope there is a diagram that's slightly larger on the next. Cool, there is. Let me zoom in a bit. Alrighty. So A turns this way, And so A is turning this way. This gear over here will obviously turn the other way. So let me draw that. It turns the other way. That's hard to see. Let me draw that in red. It turns this way, that way. And if you imagine now the rope, the chain going along like this gear is also turning the same way. The chain doesn't reverse direction, but the meshing of the teeth reverse direction. So now the gear will turn this way. Sorry, this gear will turn this way. And now that this gear is turning this way, well, naturally, this gear turns the other way because they're touching. So this gear turns this way, and it's pulling on the rope. You can imagine the rope being pulled the rope being pulled this way in and around and around and around and around. But the key bit is where it goes around like this, about the second, this bearing, I guess, this bearing block. In other words, this pulley, bearing, whatever.
Pulley.
This circular thing will rotate clockwise. This rotates anti-clockwise. And then the string goes along and pulls this clockwise. We can do the exact same thing over here. This gear rotates anti-clockwise, so this gear rotates clockwise. Cool. And you can imagine the string going down, pulling in that way. So, like the string moving like this, which is the same thing as this gear turning this way. We're almost done. Now that this gear turns this way, of course, the string is going like that. So box 2 goes up and box 1 goes down. Similarly, over here, the final circle turns this way. So box 3 goes up and box 4 goes down. And we say boxes 2 and 3 go up, and we select option B here. And let's see. It looks like you guys are agreeing with me. So that's good. I see someone asking, what does it mean that the box goes up? And this is a good question for a physics competition. But in for our math contest here, up would just mean in this direction. We're meant to take the normal interpretation of up. No pun intended with the word normal. Alrighty. So it looks like B is correct. And the suggested solution is also to draw out the direction the gears are going. And note that boxes 2 and 3 are pulled up. Woohoo! Nicely done.
Okay, let's see what Martha is doing. Martha chose one of the 5 structures below and combined it with the structure on the right. The table shows the number of cubes in each column in the combined structure when seen from above. Which of the 5 structures did Martha choose? Okay, interesting. Okay, this is going to be quite tricky because my drawing skills are not that good. Neither are my visualizing skills, but let's give it a go. So I see that, like, if we think about just like, let's draw a grid here, a square representing what we already have. We can think about, here's how I'm going to think about it. I'm going to think about like what squares I already have. Like I have 3 in this column. I have 2 here, 1 here. So if I were to, put this on my grid right now, I have 3, 2, 2, 1. And I'm going to think about what I need to add to this grid and which of these blocks like does that. So I see here that in the right corner, I need like a 3, and all of these have that. So that's not much help. So we can kind of ignore this 3 because this 3 is given to us by all of them. And I see that we need to have a 0 in the bottom, like in the bottom row here. And like, for example, option C, it has 1 here. So there would be a 1 if I included C into my diagram, which is right here. So it can't be C. And it can't be A because A also has 1 right here. So that's good. We deleted some options because of that. And now we can move on to 1. I need a 1 in the middle. And if we look here, B gives us a 1 in the middle. D gives us a 1 in the middle. E also gives us a 1 in the middle. So that's not quite helpful because all of our remaining options give us that. I need a 2 right below the 3. As we can see here, this is where the 3 would be, right? In the top left corner, my stack of 3. So the 1 right below that in option B is just a 1, but I needed a 2, and I have a 0 currently. So if I added B to what I have right now, it would only get me to a 1. So B is also not the right option. Similarly, E has nothing there. So I would stay at a 0, which is not what I want. So D is the only one that works. But just to be safe, for fun, let's check that the bottom left corner is also satisfied. I have a 0 currently. I need 1, and we get a 1, so that works. So D is the correct option. Okay, let's see if this is right. It is D. Okay, successful.
Nice. That was a fun problem. 3D visualization is always fun. But I liked that solution as well.
Always tricky.
Oh, yeah.
I must say as well.
Alrighty, but the stakes are higher for this question because there are 4 of them. That is 4 stakes placed along a 120-meter track, as shown. We want the smallest number of stakes that could be added such that the track is divided into sections of equal length. So basically what this question is, what we first need to find is the spacing between stakes. Well, a problem we see right now is that if we just try to space everything 24 meters apart, sure, that would work. But then we would get a stake at the 48-meter mark. So it would be 18 meters away from 30, this second stake, and we would need to put more stakes in. And this seems like an altogether inefficient way of solving the problem. But suppose each of our stakes were k meters apart, variable k. Well, we know that k is a divisor of 24. That is, well, we have some number of stakes between the first stake and the stake at the 24-meter line. This line just means divides. K is a divisor of 24. 24 is a multiple of k. Similarly, 54 is a multiple of k. Or rather, I think something more efficient to say would be that 30 is a multiple of k. Yeah, I saw someone mention this as well, because, well, we need to have an integer number of stakes between this stake and this stake. So, well, k, some multiple of k will be 30. Similarly, some multiple of k will be 66. So in other words, we need to find the largest possible number, since we want these stakes to be as far apart as possible. So we want the largest possible number that divides all of 24, 30, and 66. The largest k that divides all of these. And I see someone in chat has said a keyword, greatest common factor. Yes, this is in fact called the greatest common factor, 24, 30, and 66. And I also see Jocelyn, Caroline, Nikhil, Caroline, again, and more people. But there's so many of you, I can't even read your names fast enough. This is awesome. But k is 6. So in other words, the spacing between every single stake will be 6 meters. 6 meters between stakes. All right. Now let's find how many stakes in total we need. Well, our track is 120 meters long, so we would need 21 stakes total. Does this make sense? We'd have one at the 6 times 0 mark, 6 times 0, 6 times 1 mark, 6 times 2 mark, all the way to the 6 times 20 mark. So we'd have 0 through 20, or 21 stakes. That is called a large dinner. But we have 21 stakes, and like people are saying, we're not done there. We can't just say 21, because we already have 4 stakes. So we need to add only 17 more stakes. A very, very filling dinner indeed. 17 stakes. And if they happen to be silver, well, then you can keep vampires off your track as well, which is, isn't it? 17 stakes.
Thing? Vampires don't
I
like
think
silver.
if you... Oh, I thought vampires are afraid of silver because they can see their reflection in the silver. But
I'm not aware.
Maybe I would be misinformed in this.
Maybe Evan's a vampire.
I'm not. No, I don't like the sunlight for other reasons.
Okay. Ooh, we're on number 26 now. We jumped ahead. I think. What problem was the previous one? 24. Okay, maybe not that big of a jump. Interesting. Anyway, let's see what Martin's doing now. Martin has some cards. 3 of them specifically. With numbers written on both sides. The card with number 1 has a 1 on the front, a 4 on the back. A 2 has a 2 and a 5, 3 has a 3 and a 6. Martin randomly places all 3 cards on the table and adds up the 3 numbers he sees. How many different sums can Martin get? Martin randomly places all 3 cards on the table and adds up how many different sums can he get. Well, to me, it seems like we only have 2 options for 1, 2, and 3. So why not try them all and see how many different sums we get? There's only 8 cases anyway, which is not bad. So let's say card 1 is front, card 2 is... Okay, let's say all 3 of, like, card 1 is front, card 2 is front, card 3 is front. We'd get 1, 2, 3. Gives me a 6, right? Now let's say card 1 is front, card 2 is front, but card 3 is back. We get 9. Okay, so now let's say 2 is the one that we flip. So let's say we have 5 here, but then we're going to go back to 3 to make sure that we get, like, hit every case. Hold on. I'm counting this and not in a good way. Okay. How should we do this? Well, let's go 1, 3, 6. Okay, this is fine. And now I'm going to keep 1 the same. Actually, here's what we're going to do. Just to make this very organized, that I don't miss anything, we're going to split our cases into sub-cases, which makes things more clear, which are flipping one card or flipping two cards, if that makes sense. Or like keeping two cards the same. So in our first case, we're keeping two of them the same. So we can keeping two of them on the front while flipping the third one. So for example, we could keep one on the front and three on the front, but flip five. This gives us a 9. And we can keep like 2 and 3 on the front, but flip 1, which gives us a 4, 2, 3. I feel like this is a very confusing way of doing this. Anyway, now what we can do, okay, 1. What we have, when we keep 1 on the front, we have 4 other cases. So let's just see what the fourth one here is. So we have 2, 5, 2, 3, 2, 6. We have 5 and a 6, which gives us a 12. Okay, this is a better way of doing this. Now we can keep 4, flip the front one, and run through all of these possibilities for the other ones again, because they're the same. So we basically have 2, 3, 4, 2, 6. And I'm not going to add these up right now because these sums are just going to be the same as these sums, but add 3 to all of them. So for the first one, it's just going to be plus 3 of the first one because we're moving the 1 to a 4, which is a 9. And this is going to be 9 plus 3, which is a 12. This is going to be a 12, and this is going to be a 15. And we have 9, 12, 15, and 6. 6, 9, 12, 15. So we get 4. I wonder if there's another way to do this, because the numbers 6, 9, 12, and 15 seem quite nice or something.
I think there is. We could suppose we start with all of the cards front up. Then if we flip one of the cards, that's the same as adding 3 to our sum. Whichever card we flip, flipping any of these cards adds 3 to our sum. And then our options are, well, then what are our options that we choose from?
That's a very nice way of thinking about it.
Yeah. So we either add 0, which is keeping them all front up. We flip one card, flip 2 cards, or flip 3 cards. So the sum is either 6, 6 plus 3, 6 plus 6, or 6 plus 9. And this is another way inspired by, obviously, to get 4 options.
I think this is an important lesson. When you do a problem, and however you do it, you get a nice answer. I mean, like, when you're doing sums of random stuff and you get all multiples of 3, like, I didn't know Evan's way. Like, I didn't see that. But I saw the numbers and I was like, there must be another way to do this. Or there must be something more going on. Because 6, 9, 12, and 15 aren't too nice to just be a coincidence. And you should probably try to figure out the way Evan did, because let's be honest, that's a much nicer solution, more pleasing, and you probably learn something more along the way.
Yeah,
anyway,
I agree. Especially in Math Kangaroo problems, which are set up to have an elegant way of solving. But I see people have started mentioning the time, and just like all good things, this live solve must also come to an end. So it is the end of the hour. It was really fun to have you all here. But yes, goodbye, and we shall hopefully see you in a class or in a future live solve. And if you had fun today, please don't hesitate to, check out live.poshenlow.com for classes taught like this, except with real input from Professor Lowe, and a similar 2TA setup with Chat Relay. It seems like you had a lot of fun. So thank you all for coming.
Yep.
Let's
Thank you
see.
for coming. 45 stars. That's a. Is that the?
Nice.
Oh, someone got 61. That's.
Woo!
You get MVP.
I see a question about infinity. And I think in the remaining time until the stream ends, we could just answer this question about infinity. So like infinity, there are many kind of different types of infinity.